another video in this channel. So in this video we are going to be looking at the topic curve sketching, specifically for further math students. So we are going to be solving a tutorial question. This tutorial question is actually a question from June 2021 for the math paper 2, and it was question number 9. Alright, so let me display the question and then we get the solution. So the question reads, a function f defined by f of x equals to the ln of 4 minus x squared. Roman 1, find the domain of f. Roman 2, find the limit as x tends to negative 2 from below of f and the limit as x tends to 2 from above of f. Roman 3, investigate the parity of f. Roman 4, find the asymptotes of f. Roman 5, obtain f prime of x, that is the first derivative of f with respect to x, and hence determine the stationary points. Roman 6, draw the variation table of f. Roman 7, find f double prime of x, that is the second derivative of f with respect to x, and show that f of x has no inflection point. And finally, sketch the curve y equal to f of x. So that is the question that came in June 2021 for the math paper 2 question 9. Like I said, it is for further math students. Though math students can still go through, but it is a little bit advanced. Alright, so we are going to begin by looking at the solution to exercise, that is question Roman 1, Roman 2 and Roman 3. Alright, so let's begin with the solution to Roman 1. Now Roman 1 is asking us to find the domain of f. So let's first start by defining what the domain of the definition of the function is. So the domain of f of x are the values of x that makes f of x to be defined, or that makes f of x to exist. Now our f of x has been given as the ln of 4 minus x squared. So generally, when is the ln function defined? So for the ln of g of x to be defined, then g of x should be greater than 0. That's basically. Alright, so in this case we see that our g of x is what? 4 minus x squared. So for the ln of 4 minus x squared to be defined, 4 minus x squared should be greater than 0. Being greater than 0 means that you are positive. I know that only the ln of positive numbers exists in a set of real numbers, because here we are dealing with functions defined in the set of real numbers. Alright, so 4 minus x squared greater than 0, we can divide all through by negative and we get x squared minus 4 less than 0. Alright, from there we can do difference of 2 squares. Here you have x minus 2 into x plus 2 less than 0, and you get this as your solution set. Negative 2 is less than x less than 2. So we can write it in the interval notation as x belonging in the interval from negative 2 to 2 with the bounds being excluded. It's very important to always put your domain in this format so that you can easily identify the bounds. Here our bounds are negative 2 and 2. Alright, Roman 2 is asking us to find the limit as x tends to negative 2 from above of f of x and the limit as x tends to negative 2 from below, or of 2 from below of f of x, sorry. Alright, so we know that if you use a substitution u equal to 4 minus x squared, clearly as x tends to negative 2 from above, our u tends to 0 from above, because splitting x with negative 2, when you square it, it becomes positive, and it is going to go from up. It's actually going to be negative 2 is going to be positive 4 from above. So 4 minus 4 from above gives us 0 from above. Now also, as x tends to 2 from below, our u is tending to 0 from below, because putting x as 2 from below, when we square it, we get 4 from above. 4 minus 4 from above gives us 0 from above. Now let's take a picture of a graph of the ln of u, because since we have changed our variable, here we are going to have the ln of u, not the ln of 4 minus x squared again. Now this is the ln of u, and we are supposed to find out the limit as u tends to 0 from above of the ln of u. That's what we are looking for since we have changed our variable. Now this is a graph of the ln of u. It is increasing. You see that u tending to 0 from above, it means that you're coming to the right of 0, as u is approaching 0 from above, coming from the right, we see that the limit of u is tending towards negative infinity. So clearly, the limit as u tends to 0 from above of the limit of u is negative infinity. Now from there, we can deduce our limits here already. So in this case, we are going to have negative infinity because this is the same as this. So this limit here, that's the limit as x tends to negative 2 from above of the limit of 4 minus x squared is the same as the limit as u tends to 0 from above of the limit of u. Likewise, the second limit is still the same. So we see that these two limits have the same value, negative infinity. Alright, Roman 3 is asking us to investigate the parity of f. The parity of a function is the even or the odd nature of a function. Now, if a function is even, then f of negative x is equal to f of x. It means f of x is going to be even. When is it odd? If f of negative x is equal to negative f of x, then f of x is odd. So we see that in both cases, all we need to do is to find f of negative x, and then we see, we compare now the relationships, and we conclude if the function is odd, if it is even, or if it is neither odd nor even. So we have been given our f of x as lim of 4 minus x squared. Now what is f of negative x? It is simply replacing x with negative x. But doing that, when you square it, you still get positive x. So our f of negative x is still the lim of 4 minus x squared. Now since f of x is equal to f of negative x, as you have seen, then f of x is even. Since for f of x to be even, f of negative x to be equal to f of x. Alright, so we are going to move on to the solution of Roman 4 and Roman 5. Alright, so let's begin with the solution of Roman 4. Roman 4 is asking us to find the asymptotes of f. So let's first of all define what the asymptote, or let's see the mathematical definition of the various asymptotes that exist. So first we talk about the vertical asymptote. Now, we can deduce the vertical asymptote from the limits and the bounds. If the limit as x tends to a certain constant x0 of the function is either plus infinity or minus infinity, then the line x equal to that constant is the vertical asymptote. Now let's talk about the horizontal asymptote. The horizontal asymptote is gotten by looking for the limit of the function at plus or minus infinity. So if the limit as x tends to plus infinity of my function f is equal to a constant, or the limit as x tends to negative infinity of my function is a constant, then the line y equal to that constant is the horizontal asymptote. Now the last type of asymptote is what we call the slant asymptote. Now it is of the form y equal to mx plus c, meaning that it has a gradient, you see, because if the gradient is 0, then we just fall directly at the horizontal asymptote. But when the gradient is not 0, we call it a slant asymptote. Now how is it defined? If maybe I have a certain line such that if I take the function minus that line and I find the limit at plus or minus infinity and the result gives me 0, then I can conclude that that line is a slant or an oblique asymptote. Clearly, so the line y equal to mx plus c is a slant or oblique asymptote. So generally, if you are being asked to find the slant asymptote, then you need to look for m and you need to look for c, and they all have their mathematical definitions. So we are going to look at that in the videos where we are required to do that. So earlier we found the limit as x tends to negative 2 from above of the limit of 4 minus x squared gave us negative infinity. The limit as x tends to 2 from below of the limit of 4 minus x squared gave us negative infinity. So clearly we can see that what the lines x equal to 2 and x equal to negative 2 are the two vertical asymptotes according to this definition. Our x0 here is what is plus 2 and negative 2. So those are the two vertical asymptotes. Now there are no horizontal asymptote nor slant asymptote because we did not find the limit at plus or minus infinity, because the function was defined in an interval from negative 2 to 2. So clearly, since we cannot find the limit at plus or minus infinity, since it is not maybe a bound in the domain, then we can conclude already that the horizontal North-Zealand asymptotes do not exist. Alright, Roman 5 is asking us to obtain the first derivative of f with respect to x and determine the stationary points. The stationary points are also called the turning points. Alright, so at the turning points or at the stationary points, the first derivative of the function with respect to x is equal to 0. But we need to look for that derivative. Now that derivative is just differentiating my function. So to differentiate a line function, let me explain how you need to differentiate a line function. Now if my function y is equal to the line of f of x, to differentiate the function, all you need to do is to differentiate the integral and divide it by itself. So f prime of x or dy by dx is equal to f prime of x, that is differentiating the interior of the line and dividing with itself. So doing that here, my function is what? The line of 4 minus x squared. That's the function. So I differentiate the interior. Differentiating 4 minus x squared, I will differentiate 4, which will give me 0, and I will differentiate negative x squared, it will give me negative 2x. That's why I get negative 2x in my numerator. Now I will divide it by the interior itself, that is 4 minus x squared, and I've gotten the first derivative. Now I need to determine the stationary point, and I know that what? At stationary point, that derivative is equal to 0. So setting that derivative is to be 0 is the same as setting this to be 0. Alright, so I can cross multiply and I just get negative 2x is equal to 0. So x is equal to 0. So that is the x coordinate of the stationary point. Now we need to look for the y coordinate of the stationary point, and then we get the point itself, because the point is represented as x, y. So getting the x coordinate, we need to look for the y coordinate. The y coordinate is simply f of 0, fitting 0 in my function. So fitting 0, I just get the line of 4 minus 0 squared, which is the line of 4. So the y coordinate is the line of 4. So the stationary point is the point, I can call it s. The x coordinate is 0 and the y coordinate is the line of 4. Alright, so finally we look at the solutions to Roman 6, Roman 7 and Roman 8. Alright, so let us begin with Roman 6, which is asking us to give the variation table of the function. Now the variation table is a table that shows you how the function varies. Meaning, generally, it is a table that contains the domain of definition of the function, the various asymptotes to the graph of the function, and the intercepts if there exist. Now I begin by putting my domain of definition and the turning points, basically the intercepts as well, because we can see that what our function was defined in this interval from negative 2 right up to 2. So automatically, since we saw that x equal to negative 2 and x equal to 2 were asymptotes, vertical asymptotes, that's why I'm putting it in black, meaning that the function cannot cross. Now, between this interval, we can look for the intercepts. When x is 0, it falls directly to be our turning point, because previously we saw that the turning point is the point 0, line 4. So the point 0 is both a turning point and an intercept. Now, we need to look for the sign of f prime of x in order to get the monotony of the function, meaning to look for the intervals where the function is increasing and the intervals where the function is decreasing. So for a function to be increasing, then this first derivative should be positive, that is monotonic increasing, because when the derivative is 0, then that's the turning point. Alright, for the function to be decreasing, then this monotonic decreasing, then this derivative should be less than 0. So in these various intervals, we need to look for the sign of this derivative. Being less than 0 means that you are negative, and being greater than 0 means you're positive. So we need to look for the sign of this derivative in this interval. So that interval is the interval negative 2 right up to 0. So we pick any value in the interval and then we check for the sign. This is our derivative. We differentiated earlier. We got negative 2x over 4 minus x squared. So in this interval, we can pick negative 1. Negative 2 to 0, negative 1 is involved. So picking negative 1, we we take f prime of -1, we just get negative into 2 times -1 divided by 4 minus -1 all squared. So it means f prime of -1 is equal to get when you simplify. So to get is positive. It means that in this interval, my first derivative is positive. Now let's go to the next interval. The interval from 0 right up to 2. We pick anything, let's pick 1. We pick 1, you look for f prime of 1. You get -2 into 1 over 4 minus 1 squared. So doing it, you get -2 So clearly it is negative. So in this interval, my first derivative is negative. Now the shape of my function will depend on the sign of my derivative. Like I said, if the function is monotonic increasing, then the derivative is positive. Or if the derivative is positive, then the function is monotonic increasing. If the derivative is negative, then the function is monotonic decreasing. Now we also need to impute what? The limits at -2 and the limits at 2, because we need to know where the function increases to. We need to know where it begins its increasing nature and where it ends, and also for the decreasing nature. So in this case, in this interval from -2 right up to 0, the first derivative is positive. It means the function is monotonic increasing. Alright, we found the limit at -2, it was -infinity. So it means the function increases from -infinity right up to, now at 0, the function takes the value ln 4, because that is the turning point. So you clearly see that what this is the turning point. So at 0, it takes the value of ln 4. So it means it increases from -infinity, that is the limit at -2, right up to f of 0, and f of 0 is ln 4. Now in this interval, the function begins in the interval 0 to 2, the function is negative, meaning it is decreasing. But where does it decrease? Where does it decreases to? So you see that it decreases from ln 4 and it ends at what? It ends at -infinity, because -infinity is the limit of 2 as x approaches 2 of the function. So clearly you see that what? It increases and then decreases. So this turning point here is called a maximum turning point, and you can clearly see that it is actually a turning point because the function changes sign as it passes through that point. So that is the variation table of our function. Alright, so let us begin with Roman 7, which is asking us to first of all obtain the second derivative of the function in respect to x, and then we show that the function has no inflection point. So the first derivative we got earlier was given by this. So the second derivative is just gotten by differentiating this first derivative with respect to x. So we use the quotient rule. Now the quotient rule is saying that what? We keep the numerator, we keep the denominator first. I have just kept this negative sign outside here so we don't get confused. So we keep the denominator, which is 4 minus x squared. We differentiate the numerator minus. We now keep the numerator, which is 2x. We differentiate the denominator and we divide it by the square of the denominator. So doing this, we obtain this, and then simplifying, we get this. Now the second part is asking us to what? Show that there is no point of inflection. But what happens at the point of inflection? At the point of inflection, the second derivative is equal to 0. So showing that there is no point of inflection, we just need to show that that second derivative can never be equal to 0. Now let's try to show that that second derivative cannot be 0. Now, if a ratio is 0, then the numerator of that ratio is automatically 0. So something divided by something is 0 if the numerator is 0. The denominator should not be 0, because if the denominator is 0, the function is not defined. So basically, for a ratio between two terms to be 0, then the numerator of that ratio should be 0. So showing that this second derivative cannot be 0 is equivalent to showing that this numerator cannot be 0. So that is another way to show it. But I'm going to show you basically how we are going to show that this function cannot be 0. Alright, so we know that what? That x squared itself is greater than or equal to 0. If you square any number, it can be greater than, it is always positive, meaning greater than 0. And it can be equal to 0 if the number is 0, 0 squared is 0. So if we multiply both sides by 4, we get 4x squared is greater than or equal to 0. Because the left hand side multiplied by 4, you get 4x squared. The right hand side still gives you 0. Since 4 is a positive number, the inequality sign still remains greater than. Now if we add 8 on both sides, you get 4x squared plus 8 greater than or equal to 8. Alright, so you see that word 4x squared plus 8 is greater than or equal to 8. So you clearly see that 4x squared is automatically always greater than 0. It can never be equal to 0, but it can be equal to 8, because we have 4x squared plus 8 being greater than or equal to 8. So being greater than or equal to 8, it means that what? It is 8, 9, and so on and so forth. It means it can be 8, it can be 9, it can be anything that is greater than or equal to 8. So automatically it can never be 0. So clearly it is always greater than 0 since it is greater than 8. Now what about the denominator of our second derivative? 4 minus x squared all squared is still a certain number all squared, and it is always greater than 0. I'm not going to put equal to 0 here because our x can never be equal to 2, because for this square to be 0, then the interior here should be 0. You see, but this interior here can never be 0 because of our domain of definition. We had the ln of 4 minus x squared. So we even define that word, that ln of that 4 minus x squared should be always greater than 0, meaning it cannot be 0. So clearly that is why I did not include the greater than or equal to 0 here. So with this, we can see that what the numerator divided by the denominator will also be greater than 0. Because the numerator is greater than 0, the denominator is greater than 0. Therefore, the ratio between two things that are greater than 0 is also greater than 0. In essence, the ratio between two positive things is also positive. So if I multiply by a negative sign so that I should get my second derivative, the inequality sign this time around is going to change because I am multiplying both sides by a negative sign. So I clearly see that what negative of this function is now less than 0. But this function here is what? This function in my left hand side is my second derivative. So the second derivative now is less than 0. So it can never be equal to 0. So clearly the second derivative is always less than 0. Hence we can conclude that what? The second derivative can never be equal to 0 since it is strictly less than 0, and hence there is no inflection point. Alright, the last part of the equation is asking us to do what? To sketch a curve of f of x. So I displayed the variation table here since we found it earlier because we are going to interpret it in our curve. Now to sketch it, I need the intercept, and clearly when x was 0, f of 0 is 4, and it was basically our turning point. Now we need to look for the intercept on the x-axis, that is when y is 0. Now when f of x equals 0, it means the ln of 4 minus x squared is equal to 0. We can take e on both sides and we get 4 minus x squared to be raised to the power 0. So 4 minus x squared is 1. We get x squared to be equal to 3, so x is equal to plus or minus the square root of 3. So clearly we have 3 intercepts. This is the first intercept, 0 ln 4. Now the second intercept, that is when x is negative root 3, our f is 0, and when x is root 3, our f is also 0. So those are our intercepts. So from there, this is the shape of our graph. How do we draw it? First, we begin by putting the domain of definition, that is the asymptotes. You see that the function is defined inside this interval from -2 right up to 2. So I plot the graph, I draw the line x equal to -2. I draw the line x equal to 2. In the example, make sure to put in dotted lines because it is an asymptote, the vertical asymptote specifically. Here I try to distinguish the two lines with green and blue. Now you see that what the function increases from -infinity right up to ln 4, and then it now decreases from ln 4 right up to right down to -infinity.